Vision transformers are reshaping computer vision by bringing the power of self-attention to image processing. In this course, Tunga Bayrak, an experienced machine learning instructor, will guide you through building a vision transformer from scratch. He'll cover everything from patch embeddings and multi-head attention to assembling a full transformer model, while also exploring how vision transformers compare to models like CLIP and SigLIP. By the end of this course, you'll have a deeper understanding of how AI models process visual data.
Welcome. In this video, we will code a vision transformer from scratch. But what is a vision transformer? So you probably are familiar with transformers from large language models. And a vision transformer is also a type of a transformer, but it can take an image as input and turn it into embedding that captures information from that image. So vision transformers allow us to embed the information from images. And because of this, we can use them with language models and give the language models the ability to see and take images as input. So our language models become vision language models, and you can give them images and ask questions about them. So your language model pretty much can now see instead of just reading from text. But how do these vision transformers work? Right now, I'm going to just give a very brief overlook, and we're going to dive deeper into it in a minute. So the vision transformers use a transformer-like architecture, but instead of processing subword tokens like LLMs do, they work on image patches. And each image patch, you can think of it as a token. So you can see the image patches here from like a bigger image. So you can think of the image as a puzzle where each piece is a patch from the image, and we embed each patch into a vector that captures its meaning and information. Then we add positional embeddings, so the model knows where each patch belongs in the image. And after that, we apply self-attention, and that allows them to interact, that allows the patches to interact and understand their relationships within the entire image. And this makes each patch context aware, meaning it understands the other patches and their spatial relationships. And to get the final understanding of the image, we use a special CLS token. And instead of directly combining all patches, this token attends to all patches through self-attention and learns to represent the entire image in a single embedding. And finally, through self-attention layers and MLP, our vision transformer produces a high-level representation of the whole image. So in this video, we will be coding SigLIP vision transformer. I will just show here. And this vision transformer model has 400 million parameters, and it was built by Google as an improvement to a very famous model called CLIP, which was built by OpenAI. But what makes SigLIP special? So CLIP originally was used with softmax loss function. But softmax loss function forces the model to compare every image with all other text descriptions in the whole batch. This is computationally pretty expensive. So instead of that, SigLIP replaces the softmax loss with a sigmoid loss, which means that the model only focuses on individual image text pairs instead of the whole batch and without comparing everything at once. This makes training way more efficient and flexible because the model learns to match images with their correct descriptions without being distracted by unrelated pairs in the whole batch. And SigLIP is pretty famous vision transformer, and it's used in Google's VLMs like Polygamma and Polygamma 2, you can see here as the vision encoder. All right, so to understand SigLIP, I think we first need to understand what CLIP is, because SigLIP is an improvement over CLIP with a better loss function. So we have an image encoder and we have a text encoder. And what happens is we have a list of images and we have a list of corresponding text pairs as well. And we feed them through this image encoder, and as a result of these images, we get image embeddings. So this dog is represented with the embedding here as I1. And the same, this image gets through the image encoder, and now it's represented with an embedding. And the same thing applies to the text as well. So the running dog, the bird on a branch, and camel in a desert, they both get encoded. They both get through this text encoder, and as a result, they have their own embeddings now. So now we have a list of text embeddings and image embeddings. And what we're going to do is we're going to take dot product of all of these image and text embeddings, and we're going to train our model to text encoder and image encoder to give us high dot products for matching pairs and low dot products for non-corresponding image text pairs. So when you look at I1, it's the image of a dog, and when you look at text 1, it's the text of a dog. So we want them to have a high dot product, and for the image of a dog, this one, and the image, the text of a bird, you want it to have a low dot product. And so pretty much for image of a dog, anything that doesn't correspond to its text, we want it to have a low dot product. And the same applies to the image of a bird as well. So we have the embedding of the image of a bird, and we have the text of image of a bird, and we want them to have a high dot product because this says bird, and this also is an image of a bird. And everything else we wanted to have low dot product because they're not corresponding. And this pattern can be seen overall, all multiplication of these embeddings, and everything that gets matched, we want high embeddings, high dot product of the embeddings, and everything that doesn't match, we want low dot product of the embeddings. And now we want to find the loss function where it forces these dot products to be high and the rest to be low. And that loss function is going to be cross entropy loss. And so this cross entropy loss trains the model, image encoder and text encoder, to give high value to corresponding image and text and low value to non-corresponding image and texts. So this cross entropy loss is going to train our image encoder and text encoder. But there's a problem with CLIP, and it's because of the fact that it's using softmax function. So what happens here is when we use softmax function, we take this image dog and we take all the corresponding text that we are taking dot producted. And what we want to do is we want to give this like a high probability, and the rest we want them pretty much 0. And we want to do it for all the image text pairs here. And that is pretty problematic because you need to have all the batch, all the corresponding text and image embeddings here calculated together to be able to find this one as the highest and the others as the lowest. And you have to do the same for on columns as well. So when you have the text running dog, you're going to look at all this column here and you're going to compare it to all these images. And after that, you will get a distribution of their probabilities, and you're going to try to make this one higher and all the rest lower. And that's the problem pretty much with SigLIP, that you cannot parallelize this easily, and you will have to look at row by row and column by column to be able to calculate this. And I will show you the math behind this right now. So this is the function, this is the math for CLIP. This is the math for SigLIP. And what happens here is in image text softmax, we have this one image here, the image of a dog, let's say, and we're going to compare it to all the rest of the text input that we have. And this is going to be one run, and we're going to take their probability, log likelihood, negative log likelihood. And what we're going to do next is we also have text to image softmax. And what is happening here is we have, let's say, one text, let's say we choose T3, which was, or let's say we choose the bird T2, and we're going to compare it to all other images here and find that only this one, the corresponding one, is going to be high dot product, and the rest are going to be low dot product values. So we will have to train it over the whole other images comparatively. And that is the problem with CLIP, that we will have to do this twice. And also, it's not symmetric. And the reason for it not being symmetric is, so you might have this I1, T2, which corresponds to dog, and T2 is bird on a branch. Their dot product is different than I2, T1. I2 is the bird on a branch, but the image of it versus the text of the running dog. So it's not symmetric, and that's why we had to do it twice. But if we use SigLIP, we will only need to do it once. And what we will be doing is we will treat this as a one big matrix and find the values from there. I will just show it in a second. So inside SigLIP, instead of comparing every row like this. Now this is from this image is from SigLIP's paper, and this is from Clip, and they pretty much explain the same thing. These are the image embeddings and the text embeddings. So when you look here, the text embeddings are here and the image embeddings are here. So in sigmoid loss, what we're doing is we're going to look at each individual dot product individually, and we're going to look at it and say, hey, is this supposed to be 0 or is this supposed to be 1? And that's pretty much what we're going to do. In the paper implementation, it's +1, and the positive values, the corresponding values are +1, and the rest are -1. But for the sake of understanding it simpler, and what's happening here is, instead of looking at all this row, taking this text one and comparing it to all the other images, what we're going to do is we're just going to look at this and say, hey, is this supposed to be 1? And if it's so, we're going to train the image embeddings in that way. And we're going to look at this one. Is this going to be 1 or 0? It's going to be 0 because it's not the corresponding thing. And we can look at all the rest of this image and say text 6 bit image 4. What is it supposed to be? It's supposed to be 0 because they're not corresponding. And when we're going to look at image 6, text 6 is going to be 1 because they are the correct image text pairs. So sigmoid loss here allows us to individually calculate each if each dot product has to be 0 or 1, and because of these partition ability, we can separate this into matrices and give each of these into a different device, and we can parallelize this process. So this allows us to be faster. All right, let's get to it. Right now, we will be starting to code SigLIP Vision Transformer model. And first things first, we will need to get our images. So let's get our images that we will turn into an embedding. So this image you see right here, the image of a cat. This image is going to run through our model SigLIP, and at the end, it is going to have an embedding that captures all the information from this image. First things first, we need to get our model to actually run this image. So what we're going to do is we're going to import the from Transformers library. We're going to import the auto processor, which is going to process our input, the image. We will import the SigLIP vision model, which holds the model weights, and it's the fully pre-trained model from the Hugging Face, and SigLIP vision config. And this is the configuration and the architecture of the model. And we will be able to tweak some parameters if we want to, like changing how many layers there are and the embedding dimensions as well. And right now here we are loading the model and its processor from the checkpoint of Hugging Face. This Google SigLIP base patch 16.2.24 is the checkpoint we are using. It means that our patch size is 16, and we are going to be using 224 by 224 images. And right here we are actually getting the whole model itself, the full model itself, from the same checkpoint. And this model is the full transformer with the weights from Hugging Face. And let's check how our model structure looks like. So as you can see, the model from Hugging Face has, you can see vision transformer and the vision embeddings. So let's look at the structure. This is the contents of this vision model, but it's not in sequential order. So first of all, we can see SigLIP vision embeddings here, the patch embeddings and position embeddings. So when we look at the SigLIP architecture, the embeddings is this green box. We have the patch embeddings and the position embeddings. So get the rest. And then we have the encoder. And this encoder is this blue box over here. And what you can see here is we have the layer normalization, multi-head attention, another layer normalization, and multi-layer perceptron, MLP. And when we look at our contents here, we have the layers. We have the scale.product attention, which is the self attention. We can see over here the multi-head attention. And then we can see layer norm 1. This was the thing right before multi-head attention. We can see then layer norm 2 right here, its content. It's exactly here. And then we have, we also have multi-layer perceptron. It has two fully connected layers, FC1 and FC2. and it has the GELU function, nonlinearity function in between. So it's inside here. And at the very end, we have the post-layer normalization. All right. So as I said, this is not in sequential order. It shows what contents it has. So we now have our image and we know the architecture of our model, but we cannot give the image directly to the model. We need to pre-process it so that we can feed it to the model in a way that it can understand. So let's get this part. So what is happening here? We have our imports and we are pre-processing the image. What happens is it takes an image and the size that it resizes is 224 by 224 pixels. So the images are being processed in here. You can see the images are being processed to get resized, and then they are turned to a tensor, and then it also normalizes them. So the resize turns all the images into 224 by 224, and then we turn it to a tensor, and then we normalize them. And you might wonder what where these numbers come from. They actually come from ImageNet dataset. So ImageNet is a dataset of more than 14 million images, and what happens there is when they take the normalization values among all that dataset, these are the values for the mean, and these are the values for the standard deviation that turns out to be the most optimal. And this is pretty much an industry standard to use these. And when we run it through the pre-process, here you can see we give the image and now we have a tensor. The pre-process over here, we get a tensor. And after that, we unsqueeze that tensor. And why do we unsqueeze that tensor? The reason for that is over here, our image right now is 224 by 224, and it has 3 channels, RGB, red, green, and blue. But if you want to turn our image into a version that the transformer can understand, we should add the batch dimension, because every time we send images into transformers, we have to send them in batches, meaning that like there's going to be a couple images. So this is the batch dimension that we have to add. Even if we have one image, we have to add a batch dimension and say, hey, there's only one element there. And then what happens is we unsqueeze it and we turn it into the correct dimensions that we need, and then we just return that image tensor. And what happens after that is we get our image tensor. So our image tensor is pretty much we're just running it through this function, pre-process image, and it takes our image and it gives us the image tensor. And the values here these are the values that Polygamma 2 configuration uses for SigLIP. So Polygamma 2 is a vision language model, and these are the parameters that it uses. So right now for this SigLIP implementation, I'll be using those parameters. So the embed dim is 768. This means that every image patch is going to be turned into a vector size of 768. So it has 768 dimensions that it can get embedded into. And the patch size is 16. That means each patch, each little puzzle piece from that image has a size of 16 by 16 pixels. And the image size is 224 by 224 pixels. That's the big image. And right now we need to find how many patches we are going to get from that image. And what we're going to do is we're going to get the image size, 224 on the height and width, and we have the patch size 16. So we divide it and we get 14. So that means there's going to be 14 on the height and 14 on the width dimensions. So when we multiply these two, we're going to get 196 patches from from the whole image. And what we're going to do after is we, without calculating the gradient here, we have no gradient. This means that we are not in the training mode and the model doesn't save our gradients for efficiency. So to simply put, our model won't save the feedback from the calculations to update convolution 2D parameters. And what happens here is with this convolution 2D parameters, we are running the image through image tensor values throughout this layer to get the patch embeddings. And what it does here is our kernel size is our patch size. That means what is the pretty much the kernel size is how big our patch size are going to be, and the stride here is also equal to the patch size, and that means that the patches that we're going to get from that image through convolution, they're not going to overlap. So by this way, we will have separate individual patches that don't have any overlapping values or pixels. And right now, let's see what our dimension is. So as you can see here, we have a batch dimension of 1, and our embed dimension is 768. We have it 14 by 14, so that means 14 patches on the height and 14 patches on the width. And in total, our number of patches is 196. All right, let's add the position embeddings. So as you can see here, we have the number of patches and the embed dimension. Number of patches is 196 and our embedding dimension is 768. So what happens is here an embedding creates a lookup table for all the positions that we have and their embeddings. And then what happens is we create the positions here, num patches for all those patches from 0 to 195. And then we expand it, adding the batch dimension we need, because otherwise transformer wouldn't be able to use them and it wouldn't be compatible with the rest of the patch embeddings. So we add this patch dimension, batch dimension, and then our position IDs now has the shape of 1 to 196, and let's see what it is exactly. So this is a batch size of 1 and it has 196 patches inside it. And now it's time to add the position embeddings with patch embeddings. So what we're going to do right now here is we had our patch embeddings, but we need to flatten them. So they are in not like a one dimension size, but we need to flatten them into batch size of 1 and our embed dimension and number of patches. So after this flatten operation, we have this dimensions, but this dimensions is not compatible for addition with the position embeddings, because our position ID shape is 1 by 196, and when we have the position IDs here, when we input these to position embeddings, what we're going to get is 1 by 196 by 768. So what we need to do is our patch embeddings needs to be the same size as these, and that's why we're going to transpose those embeddings that we have, the patch embeddings, and they were 1 by 768 by 196, and when we transpose these two dimensions here, what's going to happen is our dimensions are going to match, the patch embedding dimensions and position embedding dimensions are going to match, and right here the embeddings, patch embeddings 1 by 196 by 768 are the same as position embeddings, and we're adding them together. So right now we have all of our embeddings and their shape is going to be 1 by batch size is 1, the number of patches is 196, and the embed dimension is 768. So we're going to have that dimensions, and yes, we are correct. And you can see it here. So what we've done so far is we had our position embeddings and we had our patch embeddings. And if you look at this architecture, we had our patch embeddings and we add them with position embeddings. So our embeddings layer is right now done with adding these two together. And let's visualize what we have right now. So right now I'm gonna just get the embeddings, and I'm gonna get the embeddings from a randomly initialized embeddings. So because it should all look random, and because they're randomly initiated here. And our embeddings right now are not trained, and it just gives us this not so smooth image. And what does this image mean? So the patch number is here from 0 to 196. These are the patches, small puzzle pieces from the big image. And the embedding dimensions are going from 0 to 768. And what this means is each patch has this many dimensions in its embedding. And when you look at this image overall, you can see that it's not trained because it's not smooth and it's not uniform. So all the dimensions here and all the embeddings, they don't actually mean something. But if we compare it to the trained embeddings, so when you look at this, what we're doing is we're taking the inputs and we're running through a processor, and we're using the vision model. But what is this vision model? This vision model is from and you look at it, this vision model is from Hugging Face checkpoint. So this is the trained embeddings. So this embedding, when we run it, we're going to see a different result. What you see here is the embeddings that we got from the Hugging Face checkpoint. They are more smooth, and you can see that they are normalized. And what these columns you see here are in specific dimensions. They have some relations, and they are representing some specific features. So the difference between untrained patch embeddings from our embeddings that we just randomly initialized versus the embeddings that we took from Hugging Face checkpoint are different in the sense that they're not uniform and smooth. That means they are not representing the image and image patches as they are intended to. Right now, let's make everything look more neat and wrap everything in a class. So here I create a data class to store the vision configuration. So our number of channels is 3, our embed dimension is 768, our image size is 224 by 224, and each of our patch is 16 by 16. So this configuration, we can change it if we wanted to, and I'm just putting it as the config class. And SigLIP vision embeddings, this class over here, this class is pretty much this vision embeddings that you can see here. And it is the patch embeddings and it adds the position embeddings. And let's look into this one. All right, so what we have right now is the initialization, the config values, we initialize them, and number of channels, it was 3, embed dimension, from here we get 768, image size is the same, and patch size is the same as we defined here. And what happens here is we are also assigning the patch embeddings from convolutional 2D, which was pretty much getting all the patches from our image. And the number of patches we found was 14 by dividing the image size by the patch size and multiplying the height and the width. And our number of positions on the image is the number of patches. So however many patches there are, there's that many positions. All of these we have already done above, and it's just wrapping everything into a class. And the position embeddings are then embeddings from how many positions there are and how many embedding dimensions there are. So we initialize that, and we pretty much create that with compatible dimensions to add these position IDs with the batch position embeddings with the batch embeddings. And we did all of these here actually. So these were the position embeddings, and these were pre-processing the image, and the patch embeddings we got from here, the convolution 2D, is the same thing we're doing right over here. So what we're doing pretty much is just wrapping everything in a class. We're not doing anything new. And in the forward, what we're doing is, so we get the pixel values and we assign it to batch, channel, height, and width. So our patch embeddings are the pixel values after we run patch embeddings. And what we do with them is we flatten those patch embeddings. So we got the patch embeddings, and then after that we flatten them here. After flattening them, we transpose it to be able to add the position embeddings on top of them so their dimensions match. So as you can see, we have the position embedding addition here. And after that, we add patch embeddings with position embeddings, and now we have our final embeddings. And what that means is now we can feed these embeddings into the encoder layer and get our image to be actually worked on inside the transformer. So let's try it. What we're gonna do right now is we are gonna have our SigLIP vision embeddings from our vision configuration. You can see here as the configuration that we did, and we have our image tensor, over here that why can I not see it? All right, so the image tensor, we are also feeding it in here, and it is the image tensor after pre-processing. So what we're doing is we are feeding that image tensor inside this embeddings, and now we are hoping to get the shapes of the embeddings. And what do you think these this shape is going to look like. So our batch size is 1. How many patches we have? The number of patches is 196, and what's the embedding dimension? It's 768. So since we added the patch dimensions to patch embeddings to position embeddings, and they have the same dimension, we transpose the patch embeddings to be able to add it to each other. So we are expecting to have 1 by 196 by 768, and let's see exactly. So this means our embeddings are actually getting added, and it's working right now. So right now, I think we should do a sanity check. Let's see if we actually initialized our embeddings properly, and if we are able to get load the Hugging Face weights and get the same answer. So what we're doing here is we have our state dictionary. It's embeddings that we have, and we are getting its state dictionary. It means we're getting its weights and biases. And we have the Hugging Face state dictionary. It's the weights from Hugging Face for the vision model that we define at the very top, the thing that we got from Hugging Face. So this is the Hugging Face's own weights. So we're trying to check if we initialized and created everything properly, so that we can actually take Hugging Face values, weights. So what happens here is we're going to get the difference between our output and Hugging Face output, and we're going to do a sanity check pretty much. And when we run it, what it says is the difference between our output and Hugging Face output is 0. So what that means is we implemented it correctly. So we are at the right track of creating this. All right, now that we have the embeddings now, it's time to actually go into the encoder. So as you can see in our architecture, we finished implementing the embeddings. We had our patch embeddings, we flattened them, we transposed them, and then we added the position embeddings. Now our embeddings are complete, and now we need a way to process them, and that is going to be through the encoder layer. So inside the encoder layer, we're going to start implementing it from the multi-head attention, and let's get into it. So, all right, so we have our multi-head attention here, but we're going to implement it in a vectorized way to match the attention weights. But to make it simpler, we can start with implementing a single head attention first, since it's a little more intuitive doing it this way. So here we are setting the head size here. This is the size that we will project our tokens into each head. And after that, we are going to create 3 linear transformations. So these linear transformations are key, query, and value. And these are the core components of self-attention. So these 3 transformations actually let patches interact with each other. So any patch from any part of the image can interact with each other through these key, query, and value transformations. And what we have in the forward pass is, so this from the shape of the image embeddings, we get the batch size, we get how many tokens there are, and we get the embedding size, the hidden dimensions, or you can say. So, but here's where the magic happens. So every token from here, every patch from 196 patches, each of them are going to embed, are going to emit 3 different vectors. So the first vector is key vector, and it represents the information that this patch, this token contains. And the second vector is a query vector, and this represents what information this token is looking for. And the last one, the value, here is what the this is the value vector, and it's what actually gets aggregated if there's a match. So how you can think of it is key, each patch says I have this, I have that, and query is each patch is looking for something. And if these get high value when they're matrix multiplied, that means that they are attending each other more. So now we can calculate the attention scores here, and through matrix multiplication of queries and keys transposed. We are transposing the keys to be able to do the matrix multiplication, otherwise the dimensions don't match. So, and this is through this matrix multiplication, we get the affinities between all tokens. And we scale it by square root of the head size to prevent dot products from growing too large. And this is scaling, like pretty much normalization, you can think of it. And then here we have the softmax, and this softmax turns the raw scores into probabilities. Like it didn't clip, it take vector and it turned into probability distribution. And after that, each row will sum to 1, and it's going to give us a proper attention distribution of each patch. And after that, what we're going to do is finally we can use these attention weights to aggregate the values. And this weighted sum here, it allows information to flow in between tokens. And this output is what we're returning from this forward pass. And now we can actually implement the full multi-head attention. And what's going to happen with that is, so we just looked at what happens in a single attention head, and it's pretty much all the tokens attend to each other. They have their key, query, and value vectors, and they get their dot products, how much their affinities in between each other. And now that was one head, but we're going to do a lot of these in parallel, and that's what we call multi-head attention. So here we have the head size initialized and number of heads initialized, sure. And in this one, here we create multiple attention heads. So we said number of heads here. So we are pretty much creating like running through this number of heads, and each head can learn to focus on different types of relationships between images. One can focus on the colors, some specific colors, the other can focus on some other specific textures or whatever they want. So each head can focus on specific features and different relationships between these patches. And after that, we are concatenating all heads, and we need to project back to our input dimension. So whatever input we got, we have to output the same dimension. And this lets us connect back to the residual pathway in the transformer. And what residual pathways are here is what you can look at is, so we have our multi-head attention here, and we had the residuals from right after the embeddings, and we want to be able to add these here, so they have to, the output of multi-head attention has to be the same as the residual that's coming in, and that's what projection does. So from this linear layer, the input and output is going to be the same. So what we've done so far is we implemented a single attention head, and then we created multiple attention heads and we concatenated them together. And the reason we use multiple attention heads is the more heads we have, the more interesting features and relationships we can capture. So to be able to match the output dimension that we expected, we concatenated those attention heads, and now we were able to use those multi-head attentions and make it work with our model. But this is not how Hugging Face does it. To be able to use Hugging Face weights, we need to implement it the way Hugging Face implements it. So if you look at our configuration, it's pretty much the same, nothing changed here. And let's look at the SigLIP attention module. And here we are implementing the multi-head attention mechanism in a vectorized way. So this is different from the previous implementation where we had separate heads. And here we will process all attention heads in parallel, and we're going to do it because it's more efficient to do it that way. And that is how Hugging Face does it, so because we want to be able to use their weights. While we could keep the implementation cleaner, actually, with some other multi-head attention implementation, it's definitely better to keep it the same way with the original implementation. And so we can load the weights from the Hugging Face model easier, and we don't have any problems with that. So here you can see key, value, and query projections. And unlike our previous implementation with separate heads, we're using single projection layers this time. And we will later reshape their outputs to handle multiple heads in parallel. And this is actually more memory efficient, and it follows the standard transformer implementations. And you can, again, get the value, the weights from Hugging Face exactly if you implement it the way they do, through vectorized. And in the forward pass, the hidden states and the embeddings and of the patches here again are just given to those variables. And what we do is first we project our input to query key and value vectors just like before, and each patch in our image will again emit these three vectors, and they will be used again for attention just like before. But now the different part here is here, like this is the important part, we are reshaping multi-head attention here. So instead of having separate heads like before, we are splitting our embedding dimension, and imagine we're taking our large embedding vector and splitting into num head pieces. So here we had our batch number, we had how many patches we have, and we have the number of heads, how many number of heads we have, and this is the embedding dimension was 768 divided by number of heads. So we have one big vector of query and key and value, and we divided it between number of heads, and we take one big vector and we divide it instead of concatenating all those different attention heads together. So this is what we do differently, and this allows us to get the Hugging Face implementation and their weights. And after that, we have the query and value settings, and we then get the matrix multiplication of query and key, just like before. This gives us the attention scores of each patch, and we again apply softmax, just like before, to find the distribution of the probabilities. And after that, we also have some dropout here. And this dropout is for regularization during training. And this helps us prevent our attention patterns from becoming too rigid. And this also helps us with avoiding overfitting. And after that, we have our attention outputs, our attention weights multiplied with our value states. And this is just like the same before. And after that, finally, we can actually reshape everything back to our original dimensions, and we are transposing it just like we did in the previous implementation. And we will also make sure our tensor is contiguous in memory for efficient computation. And that's what we do here. This is important because operations like transpose can make memory layout very inefficient. And this contiguous helps us with memory actually and computation efficiency. And we have one last projection to mix all information from all heads together here. And this lets the model combine the different patterns each of these heads found. And then we return the attention output. And actually, right now, let's test our implementations with a realistic example. And we will use a typical vision transformer dimension. So we will use a batch size of one example, one image. Our num patches is the same, and our embedding dimension is the same. So let's create an example. And we here create a random batch of embedded patches to test our attention mechanism. So we set up our vision configuration with this standard transformer parameters again. Attention heads, we're going to use 12 attention heads, and our hidden size is the same as before, embedding dimension. And finally, let's run our test input through the attention layer here, and we'll be giving our config for the attention, and it's going to take the hidden states that we provide in the beginning of this encoder, and it's going to give us the output. And if everything works, our output should have the same shape as our input. And let's run it. So what we can see here is our input shape was 1 by 196 by 768. Our number of patches stayed the same, and the embedding dimension didn't change. So that means our implementation was successful. All right, so far we've implemented the multi-attention as well. And now we want to do another sanity check and see if our model parameters match with Hugging Face's parameters, and we try to download and get the same output. So what we're going to do is just another sanity check, pretty much. So we get the state dictionaries from the Hugging Face model, and we get the vision model state dictionaries. So these are the pre-trained, this is the pre-trained model from Hugging Face. And then what we're going to do is we're going to get our own state dictionary, and this is from the attention state dictionary for the multi-attention. And what we're going to do is we're going to create a mapping between our keys and Hugging Face keys, because we want to load these values, these weights from this address into this key in our implementation. So we want to make sure the weights go into the correct places. So that's why we show our k dot weight is the same as it's going to take the weights from this encoder layers dot 0 self attention k proj weight keyword from the Hugging Face implementation. So this is to make sure our keywords match. And then what we're going to do is we're just going to copy over the weights, and into our from Hugging Face state dictionary to our own state dictionary, and then we're gonna load the state dictionary into our model here, and after that we're gonna verify if the output matches. So what happens is our output just gets the output tensor, and we also get the Hugging Face outputs from Hugging Face's vision model. And what we're going to do is we're going to compare the difference, and here we just check if the results are close enough. In this is close, and we have a parameter here called atol, and that's for if that's an upper bound for the discrepancy, and if it's lower than this number, we call the difference as 0. And let's try if we manage to load the parameters properly. And as we can see, the maximum difference between our output and Hugging Face outputs is pretty much almost 0. That means we correctly loaded the weights into our model. Well, the rest of the encoder is rather easy, and we just need to implement the MLP layer through projecting the hidden states to some other space, but it will require us to update the config class. So let me just write it here. So what's happening here is we're creating the class SigLIP MLP. And if you look at our architecture, what we have done is we completed multi-head attention, and after that we have another layer norm, and we have the MLP, multi-layer perceptron. To write the MLP layer, we have our configuration here, and what we have is we have the hidden size as 768, and we have the intermediate size as 3072. And where does this come from? So by mapping the parameters to a higher dimension, the model can now learn more complex relations. And in fact, the representations that we learned in this MLP layer are the ones that we got from multi-head attention and even the first residuals back there. So this allows the encoder to learn richer representations. So as you can see here, the inputs that comes to MLP, it comes from this right after multi-head attention, and it also comes from this very beginning of the encoder from the residuals here. So this MLP gets both of them as input. And the initialization is, as you can see here, we have fully connected layer 1, and its input is the hidden size, which is 768, and it maps it into the intermediate size, which is 3072. So now we have a richer representation. And then in the fully connected layer 2, we take that intermediate size and we remap it to hidden size, so that our output is the same dimension as our input. And in the forward pass, we pretty much run it through the hidden states, run it through fully connected layer 1, and then we have our nonlinearity. And this yellow nonlinearity allows the model to capture more complex relationships in the data, and that's why we use it here. And then after that, we have the fully connected layer 2, and then it maps it back to the original size that we started with in the beginning of the MLP. And so we can just try this one out, and what happens is we have our vision config, and we have our multi-layer perceptron layer, and we run a random the dimension embedding, and what we're gonna get is hopefully the same size. And as we can see, we indeed get the same size, batch size of 1, and patch number of 196, and the dimension, embed dimension of, or we can also call it hidden size of 768. And finally, we can implement the whole vision transformer. So let me just paste it here. So what you can see here is we have our vision configurations again. And there's a new thing here called layer norm epsilon. And the paper implementation of SigLIP uses 1e-6 as the epsilon in the layer normalization. So to match the exact implementation, we will add this to the config class and define it ourselves. So that's the only reason. And apart from that, the rest of the SigLIP vision embedding is the same. We have our initialization, we have our patch embeddings, we have the calculation of the position embeddings, and all the rest. And in the forward pass, we have the patch embeddings, we flatten them, and we transpose them to add to position embeddings. and at the very end we add both patch embeddings and position embeddings together and we return them. So this is pretty much the embeddings, the green box that we can see, patch embeddings and position embeddings getting added together. And now we can look into the rest of this, which is the encoder layer. So let me get my camera. All right, so we will be writing, we already have this embeddings, and now we will be writing the class of this encoder. And what we will be doing here is we will paste the code for a single encoder layer. And what happens here? So in this encoder layer, we have one encoder layer, and if you look at the architecture, we can see that we have the layer norm, multi-head attention, layer norm, and MLP, and that is exactly the same thing. So we have our embeddings, we have our self-attention, layer norm 1, MLP, and layer norm 2, and after the initialization we have our forward pass. And in this forward pass, let me separate it like this, we first have our residuals, and then we have layer norm, self-attention, and then we add the residuals back in there. So it's the same as here. So we have our residuals, layer norm, multi-head attention, and we add the residuals back in there. And if you look at the rest of the forward pass, we again have the residuals, layer norm 2, MLP, and then we add the residuals back in there. And if you look at it, we have the residuals come in from here, and we have the layer norm 2, MLP, and we add the residuals back in. So if we get back at our code and we run this encoder layer, we are given an image tensor, and we are running it through the encoder, and we expect the same shape to be the output. And we can try, and we get a problem called no layer norm epsilon. But indeed we do have layer norm epsilon, so that means I forgot to run this. So we initialize the layer norm epsilon here, and then I'm running this one again. And yes, our input to the model was 1 by 196 by 768, and our output from this encoder layer indeed is the same dimensions. Now let's take a look at our vision model again, and let's check out the architecture. And so in our vision model, we had the we called the SigLIP vision transformer. That's the whole, that's the big image of what everything is happening there. We had our vision embeddings. That was the green box over here. And we had the SigLIP encoder layer. And this is one of those, this is one blue box. It's one encoder layer, and we have 12 of those. But we haven't implemented the rest of these encoder layers. So we need to do that and wrap them in a class. And the rest, we have our layer norm, we have our nonlinearity, GELU, we have fully connected layer 1, fully connected layer 2, we have our layer normalization 2, and we have the last post layer normalization. So post layer normalization and the encoder layers, those are the two things that we need to do right now. So we already implemented one of these encoder layers, and what is left is implementing all those 12. So if we look back at our architecture, we created one encoder layer, but there's 12 of them. So we can just create a class and have all these encoder layers under one class. And if we look at this, class that we just wrote called SigLIP encoder layer, that was meant for one of those encoder layers, but we have 12 of them. So we can just create a new class and call it SigLIP encoder, and this class encapsulates all those 12 layers at once. And what happens in this configuration file is that we have the num hidden layers, a new parameter, and it's called 12. And 12 is the number of layers that we have in this encoder. So that makes sense. And let me show myself again. Yeah. And here we have the class, and its initialization is the configuration, and we have the module list. So we have all these layers, all these 12 layers, and we're going to initialize it inside the module list. That's pretty much it. And in the forward pass, we are pretty much just running a for loop for each layer in self.layers, and there's 12 layers. And what's happening is we are inputting the hidden states, and we're taking the output from that layer and again feeding it to the next layer. So by this way, we are running this image embedding from 12 different encoder layers. And we can take a look at here, and what happens here is we have our encoder, including all those 12 layers, and we just input a random image embedding image vector, and then what happens is we expect its shape to be the same as the initial shape, so that we know our encoder is working properly, and when we run it, we can see that indeed our shape is still the same. Now, since we have the class for the whole encoder layer, let's create the vision transformer class and put everything together. So our SigLIP vision transformer class here is consisting of the configuration. In the initialization, we give the vision embeddings class, we have the encoder, and we have the post layer norm. And what happens here is in the forward pass, we just give it pixel values, and it turns them into embeddings, and then it feeds it into the encoder. And after that, we have the post layer norm, and it returns the embeddings from right after the post layer norm. And if you look at this architecture that we draw, we have the embeddings, and then we have the layer norm, pretty much the encoder, and then we have the post layer norm. So here we have turned all these special classes that we wrote into a bigger class that encapsulates everything in there. So embeddings, encoder, and post layer norm. And the output is the last hidden state, is the image embedding that includes all the information from that image and includes all the meaning from that image. It's a vector. So let's take a look at it here. We have our SigLIP model from our SigLIP vision config, and it's the SigLIP vision transformer that we just created. It's an instance of this class, and we give it an image tensor, and we expect it to give us the embedding that encapsulates the meaning of that image. And when we run this, we get the shape of this image tensor from the output as 1 by 196 by 768. And this is what we expected, and this shows that our model is doing the calculations in the desired dimensions. So we're pretty much done. We have our vision transformer, and you can use this vision transformer as an image classifier, and you can use this to give a lot of images and classify them into some text classes. You can use this as the vision head for a language model and turn it into a vision language model, or you can use it for some other vision and image text tasks. And so what we can do, the last thing we're going to do is, in the Hugging Face implementation, there's another class called SigLIP Vision Model, and they wrap it around another class to make it even more simpler implementation. So what happens here is we just have the SigLIP Vision Transformer as in our initialization, and in the forward pass we just run it through the vision model, and we just give the pixel values, and it just returns us the image embedding with the information and the meaning that it captures inside, after running it all through the all embedding, encoder, and post layer norm. And as you can see, we have our SigLIP model and we have our image tensor. We run it through that, and we are expecting to have the same size as output. And yes, we can see. So right now we can see that from a dimension perspective, our calculations are correct, but we also want to check if our keys are actually correct as well. And to make sure our keys are correct as well, we will check it. So what we're going to do is we're going to get the state dictionary from the Hugging Face implementation of SigLIP, and we're going to get the state dictionary from our implementation of SigLIP, and we're going to check if our keys are matching correctly and if we are loading the weights properly. And we can just run it like this, and we see that all keys match successfully. So that was a successful implementation of SigLIP model, and this is pretty much it. So just to recap everything, using a vision transformer, we took an image and we embedded it into a vector that captures that information from that image. And we can use an image transformer for image classification tasks, to turning a language model into a visual language model, adding visual understanding. And I want to thank Alper Balbay for helping me creating this tutorial, and I hope you enjoyed it. Thank you.